Okay. Can you do you know that? Still your viewers. Is that Debajish?
Yes, yes. Hey.
Sai Krishna.
Hey.
You look different, man, from the photo.
Yeah, maybe that my daughter clip.
Okay.
Anyway.
Now we have. You remember we exchanged quite a bit
Yes,
of
yes,
film.
yes,
Okay,
yes,
okay.
yes, yes.
Nice to see you face to face.
Yes,
Finally.
Sure, sure.
Yes, of course. It's coming now.
Oh, cool.
Or a little delay. Yeah, delay is there. Just oh, no, yeah. I did it. Oh. And how do you think is the same like that? I was just trying to do something else. By the way, it's now all the is the same link what you guys asked? Yeah, of course. So, but let me just like before. After you need to connect the audio. So you need to look at it. You don't dare. The back thing. The back is That's great. That's awesome. Hey, Michael. How you doing? Good to see you. All right. Yeah, well, better fix the driveway. Are you using virtual water? Yes, that's fine. Did you set the interpreter? I'll send you an email. There's a quick and easy way to do this. It only affects virtual water. So that's an easy one. So if you don't have any, we'll be back in just send an email. Yeah, it's I need to get the YouTube screen there. Oh yeah.
Where you put the keys? It's a good one. Where? On the table? Right there. You can tell it. Yeah. Last 2 weeks, that's like 4 different batch. How was that? It was Vegas. Enough said. Well, it was Vegas. I arrived and I arrived on Sunday. Scratching the tail.
You guys will start in like 3 minutes. Okay. I'm getting 17 viewers online.
Yeah, I know. So actually, Cisco from here, he asked me that. Good morning.
Okay, let's start. Oh. So hello everybody. Thanks for coming for this first meetup that we have for OpenSwitch. Really glad to see so many faces, especially the new ones that we have never seen before. And hello to everybody on the video. So we have about 20 views right now. So this is the agenda. That's what we published. We have pretty busy agenda. We're going to have many small sessions, so we will not keep you bored. We'll start with some very, very high-level architectural discussion. Basically, I'm going to talk about the same slide, about the same architecture that I generally talk on this kind of meetings. Diego will give us a glimpse into what does it mean to actually develop for OpenSwitch, how you get to the code, and what can you actually do about it. And then we'll go into many sessions. So Berit is going to talk about security, and we'll have Kabin and Barefoot presenting about what they actually contribute to OpenSwitch, how they get it to work with, how they get the ASICs or their behavioral models work with OpenSwitch. And then we'll go into obviously improvements that Jorge is going to take us into, and we'll finish with Ansible support. So we're getting Ansible and Procedure. Oh, good. So Kay is going to present and provide a demo about Ansible. So pretty busy one. Let's actually start. And I will move into my slide. I'm using slides from ONS because we just added. And oh, yeah. Just take time. So, OpenSwitch project, for those who don't know what we're actually doing. So we started this project about a year ago at HP. We looked into the landscape of all the different operating systems and hardware and white box switches. And we said, okay, there is open source hardware, the life is good, but which is always OCP compliant, contributor designs and stuff. But when you look at the operating system, it's all closed source, it's all half kind of big. We have this component, we have that component. If you want to have an operating system which is of the same class as, let's say, Cisco, Nexus OS, Arista OS, stuff like that, you just don't have it. Right? So we basically said, okay, we'll start new operating system, we'll start new community, and this community will build fully featured operating system. It will support OpenFlow, SDN is nice, everything is nice, but first and foremost, we'll just create a new operating system, which is familiar for the networking guys, not built for the server guys specifically, for those who really like to get to the look and feel about the network operating system. So it's very important for us to actually do it in a community manner. We are not trying to just say, hey, it's open source. We'll put the sources over there. Here are the sources on GitHub with some dirty corner. We're basically creating all the infrastructure to enable the community. We copied the infrastructure of OpenStack, so we have all the gated review systems, and we have Zoo and CIT, and we build all the test frameworks. We work very actively with all the ASIC vendors to create the drivers for the system. We work, all the sources are open. We work with Broadcom for them to open the APIs for the SDK because we didn't agree to have closed level of APIs. We want to make sure that our code is open source completely. So it was very, very important for us to get to this community level. And then we'll talk on the next slide what it actually means. We decided to go and create this full featured operating system, which means from our perspective is we have to support this layer 2, layer 3 open flow features. We need to get consistent configuration models, right? So it's not like if you want to configure BGP, you go this way and configure some files, and you want to configure LTP, you go to that, and BLACK, you configure some different files. One consistent way, either through CLI or to REST API or anything else, but consistent way of configuring the entire system, consistent way of troubleshooting the entire system, so fully featured nodes. One point that is going to be raised, we aligned and very specifically aligned to OpenSwitch. So we started from OpenSwitch code base and we extended it. Obviously, we have so many things to add to OpenSwitch, but we start from the same code base and we'll see the architecture that we are reusing key components of OpenSwitch. Many people are familiar with it. So once we actually start talking to people, they actually feel right at home. They understand what we're talking about, they understand how to get in, they understand how to actually configure this stuff. So it helped us a lot in getting the traction with the community. So I started talking about the mailing list, about the community enablement. We have mailing list. If you subscribe to this mailing list, the word you're going to get about 25, 30, 35 emails per day, because all the discussions are open Actually, even if HP employees talk to each other, they talk over the public mailing list because we want people to understand what is being done. All the designs are being published on the mailing list. All the discussions are happening on the mailing list. We have weekly IRC chat where people get together at the same time. And on this IRC chat, generally what happens is that we schedule some additional on-demand IRC chats. We say, okay, on Friday we'll discuss some additional topic. Code, design reviews, get it, everything is public. All the code that we are contributing is Apache to the tool. So with the exceptions of when we use Quagga, then we use GPL because that's Quagga. But everything else, whatever we contribute is Apache to the tool. We have defined releases and schedules. So right now we are getting to the end of the deal release, and hopefully in about 3-4 months we'll get to the point that it's going to be a commercially viable operating system, so something that is stable now. So many of the engineers will actually switch in April into bug fixing and getting the stability of the system in place. Diego is going to take us into Yocto and all this cool stuff about how you build the system and how you develop the system and how you develop the system. And one thing that I wanted to talk about here is that it's not just about code, it's about how you test the code. Right? So it's very important to make sure that the system is going to be in a form that is possible to actually develop while validating that we're not getting into regressions and stuff like that. So we created all this continuous integration system, and we're putting forward testing framework, Python testing framework that allows us to actually test everything in virtual and in physical. So the test is being written once, and the test is going to run both on the Docker containers and on the physical apps. For those who have physical apps, they can connect the test to their physical apps and validate that on their switches and their devices it works. So, participants. So if we talk about different companies that actually participate in this server, we have quite a few corporate participants. We're getting more and more individual contributors. There's this good presentation of some very active and passionate individual contributors. But we're getting all the ASIC vendors, we're getting companies that are interested to talk about application recognition and whatnot. So this is a good one on the corporate. So I'm the chief architect of OpenSwitch. What I'm really interested in is the architecture. And so all the other stuff I'm doing because I'm doing, but what I'm interested in is the architecture. And from the architecture perspective, on the next slide I will take you to the fancy diagram that I'm using all the time. But what was important for me to show on this one is the architecture principles. So quite a few architectural principles. One is we are going with very aggressive modularization. We're basically saying there is some component in the system, and we'll talk about it in the next slide. There's some component in the system, everybody is allowed to talk to this component, but nobody is allowed to talk to each other. So we're trying to avoid the situation where we're going to hairball of features, talking to each other and exchanging messages and trying to understand what happens. So we are going with very aggressive modularization situation. We want to make sure that if BGP fails, that's only BGP fails. And the rest of the system may not know about it, and it will just start again and it will keep going. So isolated fault domains, we are trying to make sure that not just failures, it's also about them absolutely not knowing about the existence of each other. And so if it were inside a building image which has some sort of features, though the other features should not be affected. They should work with the specific data models, and they should not know about who is actually executing towards the data models. Portability. Right? So the industry is not now going into x86, so a specific market that we are going for, the data center, top of rack, is consolidating behind x86. But there are many people in the community who are interested in different control CPUs, for example, going with Freescale, going with ARMs, going with other stuff. So one of the reasons why we chose Yocto is because it's embedded Linux. It's very easy to port it to other platforms. So we want to make sure that it's portable, but it's not only about the control experience, it's also about the ASICs. So you'll see on the next slide that we actually have abstraction layer that allows us to plug in different SDKs and allow different companies to actually innovate and provide connection to their specific ASICs. We want to be very good open source citizens. Right, so, and it's not easy when you talk about corporates, but we are going to upstream everything we are doing, and you can already see if you go to OpenSwitch mailing list, you'll see that we are submitting patches. and we are improving OpenSwitch as we actually improve components that we're using from them. We're going to upstream all of our changes to Quagga and to other projects as well. We don't want to just reuse stuff from others. We want to contribute it back. This is my favorite slide. So these different colors, but it's coming all to the same thing, right? So whatever you see in the big rectangle, that's all that is done on single instance of OpenSwitch. And in the middle, you see the most important component, which is the OpenSwitch server. So this OpenSwitch server, it holds everything. It holds configuration, it holds statuses, it holds statistics. So routes are being pushed into it, configurations are going through this OpenSwitch server. Everybody publishes information that they have to the database, and everybody subscribes. So if temperature daemon knows the temperature, it will publish it to the database. And if fan daemon wants to know how fast to spin the fans, it will actually just subscribe to the temperature information. So we have all the different daemons. All they know what's the data model that is inside the database. There's a schema, tables, columns, types, all this information. All they need to know is what is inside the database. They should not know what are the daemons that are actually pushing the information in the database. They should not know about it. So this is the main one, and we're using the one from OpenSwitch. This is the OpenSwitch server. One cool thing about it is that it has well-defined protocol. So there's RFC 7047 that defines the protocol that this OpenSwitch server actually works by. And it allows us in the future to actually do very interesting integrations. So basically, all the different agents of the system, they work through this protocol. If they want to be outside the system, they can. So if we want to integrate later on the switch with maybe, I don't know, maybe Docker daemon on the hosts or something like that, we can actually integrate it through this protocol, and they will be full citizens of the system. They can get any information they need from the system. They can push any information into the system. Now, but that's not exactly the protocol that we want to use for managing the box. Right? Not always the protocol. That's too complicated. People are not necessarily familiar with that, so that's not how people will manage the box. We're getting all this management daemons. So CLI, REST, Ansible is now working on top of REST and on top of the cursor config. So all the management daemons, they talk to the database. All the monitoring daemons. So Broadcom contributed Broadview support. So it monitors, it sucks up the data from the database and publishes it, whatever protocol it wants to publish.
Can you lower the volume a little bit because there's echo on the streaming?
The only question is how. My finger is minus and plus. I don't know channels. I will just take the microphone a little bit down. Okay. It works. Okay. So let me know if you don't hear. So all the monitoring daemons, all the SNMP and whatever stuff, they're taking that data from the database and publishing it up. On the right side, this is one of the most interesting daemons, and this is the OPS switch D. So the responsibility of this OPS switch D is to take the data models in the database and translate them into the ASIC. Push them down to the ASIC. And the most important part of it is this ASIC specific driver. So this is the plugin that allows us to actually interface with different SDKs. So we're not limiting ourselves to specific SDK. Right now we have support for Broadcom for OpenSL. But Mellanox is contributing side plugin, Cabin contributed its plugin for their own API, Barefoot contributes plugin for P4, right? So we're getting all these different plugins that allow us to run on different platforms. And in our booth and ONS, we're actually showing all the different platforms running OpenSwitch. So this is a very key piece of the system. We are reusing OpenFlow agent from OpenSwitch. It was there inside OBS with SwitchD, so we're reusing this component that will allow us to actually provide OpenFlow support. And we actually get Broadcom now to contribute the first OpenFlow use case on top of VXLAN release. On the left side, you can see all the different daemons, right? So for this layer 2, 3 protocol daemons, and by color coding, you can see that it's actually OPS adapted. So we take something from outside, but the adaptation is to connect it to the database. Right? That's the main adaptation that we have to do for anything integrated to the system. So we are using Quagga. That's the most interesting routing protocol stack, which is open source right now. There are some discussions like people from NTT. They're now working on integrating OpenGV with OpenSwitch. So as long as they conform to the same data models that we have inside the database, it's plugged in. It's just replaceable. Just take it off and you put it in. In general, if you look into integrating something in OpenSwitch, there are two options. One option is just drop it, and you can just run its Linux. So nothing bad happens, it's going to get the packets and everything is good. But if you really want to be part of the system, you have to integrate this database. That's the main thing. Right? So it's supposed to get the information from database, it's supposed to push whatever it knows into the database. That's the main item of the integration. We pay for its time, it's taking time to actually do these integrations, but we're getting the benefits of really building network operating system, not some disintegrated components. You have a question?
Why can't you could have done the other way, and then the model to be shipped to the OBSDB? That way, you can just drop all our OBGP.
So repeat the question: why not do the model through Netlink? Why not actually let everybody push into Netlink, into the kernel, and then suck it up from the direction?
So you don't have to put to SSH.
So a few points. One is kernel doesn't hold things like configuration mostly and this kind of stuff. So for example, if we talk about routing, we're talking just about FIB. That's something the kernel knows. It doesn't know about FIB. Right? So it doesn't have most of the models that you want to keep in the central location. That's A. B, changing the kernel is something which is very slow process. So if you need to add additional capabilities into the models, to change it inside the kernel, it's going to take forever. Now, to change it inside the database, it takes one review and get it. And for us to agree and to say, yes, we actually do this model. So if you look into the schema, you will see that, into this diagram, you will see that pretty much everything is in user space. So inside the kernel, this is not something that we do. This is not something that we do. This is small, for example, they talk about Broadcom, this is OpenSL KNet, which is a very small driver that basically just marshalls just registers. But otherwise, we don't do anything inside the kernel. And that's very much conscious decision. We're trying to keep ourselves inside the user space. Because later on, when you get to many companies, they want to be able to change kernels very quickly to address security problems, for example. And if you have dependencies on the kernel, and you need to have patches in order to extend some models inside the kernel, that's a big no-go. You'll be very much blocked by this situation.
Are you compromising the performance because of that?
So obviously there will be an overhead on OBSDB to going through this process. And what we're doing right now is one of the sessions that we have today, 20 minutes, it will be all the improvements for performance that we are doing for OBSDB server. So we have 20 minutes today specific to this topic. Let me just go for the first thing, the last thing, before we actually let Diego show the interesting stuff, actually how you get to the sources, how you build it, and what you actually get out of it. This is the current status. We always have all the basics covered. We have all this PCMP, routing, the aggregations, VLANs, all the basic stuff we have inside the copies, out there public. Some of the stuff like ACL and QoS that they're coming very, very soon in the next weeks. We will be as HPE. The community can continue to actually put additional stuff in, but we as HPE will probably stop contributing additional features at the end of the month, and we'll start working more on the stabilization. Making sure that it's stable, making sure that it performs, making sure that it scales. Broadcom contributed their support from day one, and they now work on developing OpenFlow support. Barefoot contributed before, Melrose contributed side flagging. At that time of the day, to prepare the slides, I didn't have the permission to publish it. So, but now, yeah, it's all public. So Melrose contributes side plugins, Kevin contributed X-Client support, and they are going to talk. Barefoot is going to talk about it, and Kevin is going to talk about it today. What it actually took them. The code right now is in alpha quality, so you can download it, you can build it. That's all good, but don't expect it to be in production ready. Right? So that's exactly what I'm saying. Starting next month, most people will go into bug fixing, most people will go into stress fixing and stuff like that. So right now it's alpha quality. You can take it, you can try it, it's nice, you can actually play with it. Obviously it has bugs, obviously it crashes in many situations. I think that's all I had on the high level. So before I go with Diego on into the hands-on, into 20 minutes of hands-on, any questions that I can answer on the architecture level? Very high level, why this project and so on. Yeah, I think it's all yours.
Are you going to share the slide?
Yes, we will share the slides.
I'll just upload them to our archive, so I'll send the email out.
We'll get to the archive and publish them on Meetup.com, yes? Okay. Even to. Okay. So you can use this microphone.
Okay. Okay. So, okay. So, how many of you have worked with OpenSwitch before? And raise your hand. Actually, let me ask, how many of you have never worked with OpenSwitch before? To build system. Oh, so we have plenty of people here getting started. Okay. So, Michael said, one of the things that we care a lot with OpenSwitch is that we didn't want to just throw the code and say, hey, here's an open source code, here's some components, let's go try to use them, right? We actually want that have a developer environment and make it really easy for developers to be able to contribute code, right? And developers could be a company that is doing like very good knowledge tagging, they're just contributing their plugins for their ASICs. Or if you are an OEM or ODM that has adding support for your hardware platforms, that you have also a very simple way to go forward. So there is a set of decisions and trade-offs that we made to accomplish these objectives. Also want to make it simple. So if you are a developer, you're using OpenSwitch in your data center, and you want to say, I want to put my own way of SEM. We have people that came and say, hey, I want to use OpenSwitch, but my data center is standardized on, I'm using Ansible, or I'm using some form of RPC or protobuffers or Tree or something to just push my configuration to my boxes. We don't support this, right? So we want to make very easy to, you can modify the code that, agents that you may want to run, and keep it really straightforward. So there's a couple decisions that we make for that, and just quick introduction of how the system works. So there are two parts to it. There is the build system, and there's also the infrastructure that we have, right? So for the infrastructure, we actually, for both parts, we didn't want to just reinvent the wheel. So we want to go with something proven that is useful for the community, and it's also kind of well documented. So for the CIT part, what we did is that we leveraged the OpenStack infrastructure. So if you're not familiar with OpenStack, one of the main advantages they have is that it's tested for a scale. So you can have multiple developers working in the system, right? And they also have a lot of configuration and workflows defined that we can build upon. And the whole aim of the quick summary of how the OpenStack infrastructure works is Gerrit as the main review system. So we have a Gerrit server where all the code that we change goes uploaded for review. So if you go to our I'm going to just quickly go over this. So you go to our review OpenSwitch.net. So at this point, you should know that OpenSwitch.net is our main website, right? So you go to review OpenSwitch.net, you will see that pretty much everything goes to review here. You can see actually here in review, we have support for introducing KVM API for its client and changes for adding for support, pretty much everything you can see is happening here in the folder. This is HP developers or our companies or individual contributors that are showing up in the code here, right? All the code goes to the review side. We have our own Git servers. So you actually can go to OpenSwitch.net. This is just for scale reasons. But we also have a GitHub mirror. So you can go to GitHub and move your code. It's just CEO friendly, right? Search engine optimization friendly. So the other part to it is that we have a Jenkins server and a Soul infrastructure that just scales the testing. I won't go into detail that. You can go into OpenStack and find the documentation, or go into the documentation and find some information about how we do that. One important part here also that's for developers is that one of the things we want to achieve with OpenSwitch is quality code, right? So the infrastructure is set up so that when we load code, we actually running, we're building it, we're testing it, we are running some regressions. So part of the workload that we're going to be also seeing there is how we run. We have unit tests, we have component tests that we're running, and we actually invest a lot in the infrastructure, in the code to be able to enable that, right? We want to put some changes, test that in a virtual environment, and be able to test it, right? So the other part of the infrastructure is the build system, right? So in traditional open source projects, you can see here, you say, oh, there's a lot of Git repos there, right? So there's a lot of Git code, and how do I put this all together, right? So at the heart of our system is our build system, so it's the OPS build repo. And for the most part, all you need to do is work with our OPS build system, right? The OPS build system is based on the Yocto project. So if you're not familiar with Yocto, Yocto is a open source build system for embedded Linux systems. That's the main origin for it. It's actually a Linux Foundation project. And the reason we choose Yocto, so actually we're having this argument at the very beginning of the project. Some people was coming saying, hey, I want you to, will be good if you can run on top of Red Hat, or will be good if you can run on top of Fedora, you can run on top of Debian, because Red Hat has their own data center standardizing on different, based on the distribution, right? So there's actually not a really good answer. You can please everybody that, this is the distro of your choice. The main reason we work with Yocto is that it gave us the ability to build a developer environment that we actually can reproduce. It's reproducible. We're building a whole system. We're a little bit in control of what goes in there, right? So that makes it simple for us. The other advantage we have is that Yocto is more suited for the cross-compilation process. So if you're OEM or ODM and you want to actually use OpenSwitch in boxes, like not x86 based, like a 450 based box, Yocto will give you support for that a lot. It's pretty straightforward to do that. Or working in a more exotic platform like MIPS or Weird Arms or stuff like this, right? So the build system is at the heart of our system. I'm actually going to show you here console. I'm going to this is my build system. So I'm actually going to clean this up just so you can take a look at it. The first thing that we do when you're working with a build system is that we configure for a platform. So if you're a developer and you get started, the first thing you need to work is you want to build an image for one of our target platforms. So if you go to our webpage, you will find a list of supported hardware, which at this point is pretty small. We actually announced last week in the OCPL that we were putting together, bringing online more hardware support for our platforms. But one nice thing about OpenSwitch, if you want to get started with it, is that we actually support virtual platforms. So we actually have 2 virtual platforms, right? Sorry, the first platform that we have that is virtual, I just click here. Let me just actually configure and just continue my conversation here. So I'm going to say make, this build system is pretty straightforward. So if you are a developer and you clone a system and say make, you try to type make. So we'll see the system is telling me that I should configure for a platform. So this is the list of platforms that we have enabled right now. So you can see we have the appliance, a couple of boxes, and this generic x86-64 machine, which pretty bad name it, but for the reason we'll have to change that in the future. So I'm going to pick a platform. I'm going to configure for appliance. I will explain you in a second what that is. So it's going to take the build system is just a wrapper of Yocto. So if you are familiar with Yocto or you're not familiar with Yocto, the heavy lifting is done by Yocto's build system. One of the reasons actually that I like Yocto is because there is pretty good documentation. You go to Yocto project page, you have our huge reference manual with a lot of explanations, pretty well documented. So if you want to understand that either there's pretty good documentation or you can also get Linux Foundation training courses is a standard, right? So it's configured, and the system is pretty much a wraparound. So I'm just going to tell it make. This is building a full Linux distribution from scratch. Usually this will take like 7 hours in a pretty decent portable machine.
The build system is worked with our infrastructure in such a way that we actually have caches in our web servers. So a lot of the things are going to hit our caches. So the build system will be pretty fast. So also we'll be running and keep our conversation. So I'm saying that we have two targets for virtualization. If you're running for a real hardware, obviously we're running for a real ASIC, so you need the SDK for that. So it could be Broadcom, Mellanox, KVM, all these ASICs that is providing the SDK and the support for the hardware. If you're running for, if we're creating a virtual platform, as it said, we actually have the initial target that we have for a virtual platform is a software data path that is based on OpenSwitch. So actually, we're using OpenSwitch, our software forwarding plane. And recently, actually, Mellanox contributed, and we're still working the process of integrating support for our P4 software data plane. So we take a P4, an ASIC writer, a forwarding data plane right in P4 language, we compile it, and we actually get an executable that is a forwarding software simulation of an ASIC right in P4. So that will be out soon, and then you should be able to switch your software forwarding plane from OpenSwitch to P4, which is pretty nice. You can see the building right now. It's actually it's not building that fast. My machine is not that fast. It's just that it's hitting the caches, so it's just unpacking stuff. So okay, so we have the software backend, and then we have two main targets for simulation environment. One target for the simulation environment is what we call the generic x86, that one I just mentioned a couple of minutes ago. The best name for that will be actually container. So this is an image that we generate running inside a container, a Linux container, think Docker or LXC or plain namespace if you're a little bit of cowboy. And we use this for simulation, for testing purposes. So when we have a container image, we actually use a framework that we wrote for this, that I will show you in a minute, that is useful for testing. And I'll go into that detail in some minutes. Then we also have the appliance image that it creates a virtual machine appliance, right? So a virtual machine appliance is an image that we actually generate an OVA file if you're familiar with virtual machine appliances that you can load either in VirtualBox or VMware, right? It could be ESX, or it could be your VMware player or VMware Fusion in your Mac. And we use this so that you can boot up an image that you can get familiar with. So if you don't really have hardware and you cannot borrow or get one of the hands or this hardware that OpenSwitch support, you can run that in a virtual machine. So let me actually show you that, and you can get a feel of interacting with it. So as Michael mentioned, OpenSwitch, we support actually multiple interfaces. We support traditional interfaces like CLI or WebUI, but we also support Ansible that we'll be talking today about it. And we also support declarative config. So we have all this interfacing, and maybe you want to play with it. All right, so I'm going to take here, sorry. Let me take this slide. So I'm going to play here. I actually just imported this image. This is an OpenSwitch image that I imported. It was created with appliance. So in this build that I have right here in the back, what it's going to produce is the appliance image that I can use when it's done with the build system. So I'm going to have here the virtual image. And one of the use cases that actually this is the first thing that we did is that you can import the image into VirtualBox, and you can have actually 4 network interfaces, and all this is documented on our website how to use it. So first port is a management interface, and the other 3 ports are data ports, right? So you can actually configure VirtualBox and reach one of the interfaces or a physical port, and you can attach to an external appliance like a traditional switch box router, and you can play with it. You can set up a BGP session or a OSPF session and see how it behaves, right? So it's pretty useful to get to know. The other nice use that I find to this is using a tool called GNS3. If you're familiar with it, this is a simulation tool, open source tool. So this one is just talking to my VirtualBox, and I just create an OpenSwitch image. So I can just create a couple of virtual machines. So you can see actually when running here image, it's creating these images or these machines in my virtual machine. So it's just VirtualBox is my backend. So let me create a couple of OpenSwitch switches here. I'm going to connect. I mentioned that they have management interface and 3 ports. So I'm going to attach the interface 1 on this switch to the interface 1 in this switch. Now let's play with it. So
I'm going to start this machine. And both are start now. So you can see both are running. Okay, so they're actually booting up. I can get a console bit. So this is my machine 1. And this is my second machine. So let's do something. Let's do layer 1. So as I mentioned, this is a Linux machine, so you can config everything. I won't go into details here, but let me go into my switch console CLI. Sorry. Both. Sorry. Okay, so let me search something like simple like LDP. So configure mode. Need to bring up interface up. So interface ETH1. Let me bring out the shutdown. Actually, this one will do the same.
Time check 4 minutes.
Okay, and then we'll do. I'll enable LDP. Something simple like show LDP stats. Get 1 cent. Another one send. Actually, this one received 1 packet array, so I can look at the information. Show LDP neighborhood info on ETH1. So you can see actually seeing an OpenSwitch port, OpenSwitch connected to it, right? So this is pretty nice to get familiar with it. You can get the web interface, play with your Ansible REST. So this is a very good way to get started if you're a developer, right? Don't need the hardware, play with it. One thing we're looking in the future is actually creating templates for this that you can have a clone network and use Ansible and just chop the configuration in and start playing with it. So it's a really nice tool. We also have the container that I won't go into details today. Build system is still going, so I won't have time to show that. But the end result of the build system will be this image. If you have a real hardware and you want to deploy it, the same process. Just maybe build, configure the platform you want, and then you can get all installer for that platform. And if you want to play with this, we'll try to train more manuals and information about how to get these virtual environments, get to play with it, get to work with it. I will take 2 minutes for questions before we run out of time.
If you have any questions, we have microphone.
Yes, will this work for switches that have more than one ASIC controlled by a single CPU?
You need you have like a chassis or you have a
Right, a chassis.
Right, Michael.
Eventually it will. So right now the focus is on top of rack switches with single ASIC, but eventually there's nothing in this architecture that depends on the actual focus.
Right.
Any other questions?
I have a question for Kay there.
Yeah, so
So this is more like I saw one comment today this morning on ILC chat, and he is an individual contributor, and his question was, what is the best way to get involved? Do you have any recommendations?
So I think the best way to get involved right now is to start playing with it, load the image, get to feel of it. Everybody has a different need. So one of the things that we are seeing with talking with me is that everybody has a different use case. I want to look at it from the declarative point of view, DevOps. I care about the CLI, I care about support for some hardware. So everybody have a different need. So interacting with the RC channel, with the mail list, is a very good start, and just talk to the community. What's your take? What you want to do with it, and see how try to see how we can get there. Right?
So probably the best way is to go to mailing list. We have 450 subscribers on this mailing list, it's very active one. So if you don't want to be overblown by the stream of emails, subscribe to the digest. But yeah, that's the main way of getting to many people. Ask questions, propose proposals. If you decided that it's something that should be discussed live, we'll have it on the weekly RC chats. Every couple of days before the RC chats, we're sending proposals. Guys, please send proposals for agenda, and people are sending and putting it on the agenda. Then we discuss it, and if we cannot finish it in this 1 hour, it will be rescheduled for additional hours just on this topic. So the main thing, first step is go to the mailing list. Just tell what you're interested in and how you'd like to contribute and what should happen. Yeah.
This image that you're running, is it running OAS data plane? Is it running OAS data plane or a P4 data plane in GNS3 or?
So this image is running right now. It's running OpenSwitch data plane. Yes. Okay. Actually, Berkeley guy here, they're very excited to see this. So they want to be running P4 data plane pretty soon on there.
So initially when we started, we used OpenSwitch as a data plane for the containers, and we didn't have the behavioral model emulators from P4. So we started with OVS. It turned out to be limited. So it was very simple to actually do simple stuff. But once you start doing more complicated things, I want to have different hashing for my CMP. And they want to have it inside the container. Okay, I need to change OVS code to do it. So many things were very, very limiting. And luckily enough, we got Barefoot actually involved in the project. They said, oh, wait a second, we have the very good async emulator, and it's going to be, and you write P4 program, and you get it, compile it, and you can run this emulator out of it. So they're contributing the code right now. Once they catch up on the features, and we actively working with them to catch up on the features that are supported today by OVS data plane, we'll switch over. We'll switch over to P4 data plane. We don't want to keep this OVS data plane. Yeah.
So is this you guys use for interoperability tests and all?
So first of all, Docker containers, we use them all the time whenever you commit code into the system. Whenever you it's not still not merge, it's going into review. It's going immediately through the tests inside Docker containers. That's first and foremost used, right? We want it to be tested. So all the protocols, there's no reason to test them, to wait for the hardware to be available to actually test them.
So let me take a quick shot at that just to give you the idea. So as I mentioned, we have the container image, right? So this is a framework that we used recently open source called Topology, right? So Topology, you can see it's in read-the-logs, actually it's in the HP networking GitHub. This framework, what we did is we created this framework that allows, here's a pretty good simple example here. It allows definition of, this is actually a test, right, in this framework. This is a PyTest, so it's a Python test. So we have a doc string that defines the topology. These are just comments. So this is the topology definition. This is a language called NML. So, and here's the PyTest, and this is using a picture. So this picture here that you have here, topology, what it's doing is parsing that and actually instantiating OpenSwitch images. Actually, it could be different images. Here is using OpenSwitch, but it could be one profile, it could be OpenSwitch container. Instantiating that in containers and running that in Docker, or actually it could be in other backends. And then you get programmatic access to the system. You can create an assertion. So actually, your test is now migrating to this framework, right? And just quickly, very quick view. So we have this framework to automate the topologies, architecture, and run test and create all this. And this is running in RSK. So we're moving this, actually, we're ramping the documentation and the community information about this because we actually have a previous framework that we just completely replaced by this. And it's getting started, so we'll have more information about this.
But that's testing. I also see many developers actually developing inside the containers because it's much easier. So if you want to integrate database with BGP or something, you don't have to go to physical switch. All this development people are doing on the containers very, very quickly.
But what about the interoperability, particularly interoperating with other network equipment?
Well, yeah, that's part of the limitation, right? The container, if you're working with container, you have to be a little bit of an expert to understand because the container is set up with.
No, I think I was asking a different question. Right?
Oh,
so if you have, let's say, you want to test with iOS, right?
Right.
How well your BGP works with iOS? Yes, definitely it can be done. Same way, right? So I don't think they're running this test right now. It's a little bit early, but we will definitely be able to check protocols interoperability using this model. There's nothing. Okay, guys, let's switch to the next slide, the next session.
We have one more question.
One more.
Do
Do you see, today, Dylan, as you're talking about the desire to move to the 4.x kernel, do you see the use of your isolated fault domains being able to allow you to build to other distributions that might be lagging behind, kind of like a CentOS 7 or something that might need to stay on a 3.x? Still being able to build and run the majority of the system, but maybe not some of the advanced functionality that the 4.x kernel brings to the table?
So the move to the more advanced kernel is still being debated. You can join it on the mailing list, right? Because there are a few trade-offs. We go to the more advanced kernel, for example. If you run Docker containers, you will have to be on the more advanced host, right? So you have to use Ubuntu 16.04, right, which is still not released, right? And you lose some functionality. Now, we are getting kconfig system in place, which will allow us to actually modify the image and cherry pick different features when we build the image. So we're putting kconfig on top of the octal. So you'll be able to get all dependencies. Actually, I didn't think about getting kernel decided based on kconfig, based on the features that actually should choose them. Maybe it's a good idea. We'll see how, need to discuss and to think about how to get it. Mainly, we wanted to move to the new version because we want to work on the multi-VRF support. And right now, kernel actually got in 4.3, kernel got the new VRF support. So that's the main driver right now to move to more advanced kernel. So, but maybe if kconfig is saying no multiple VRFs, you can actually choose the older kernel, so you can actually run it.
Right, and anyway, if you want to run on our platform, again, the different components have this feature. So you can, when you do the process of repackaging for your target distribution, you can probably disable some of this feature, like, okay, I just disable VRF support. So definitely something that we'll have to look into having integrated CAP, otherwise you won't have guaranteed work. Okay, thanks for your time, guys.
So next one is going to be Dirk. He's very active and passionate about quite a few things, right? So, but today he chose to talk about OpenSwitch security.
Right. So, yeah, Santa Clara Meetup. I'm also next to passion. I'm also geographically challenged. So, yeah. So when I was young and stupid, I used to do quite a bit of traveling. One day I ended up in northern Wales in a small town. Really nothing much to do there except visit the one local attraction, which turned out to be this Beaumaris Castle. Oh my God, what happened to that slide? Yeah, the colors are really way off, but believe me, there's a castle on there. Yeah, so I don't have a mouse pointer either. All right, so as it turns out, Beaumaris Castle is the best damn castle ever built. It's amazing. Right in the bottom left there, there was a drawbridge. You could get to the drawbridge. You could get arrows and things fired on you from both the inner wall and the outer wall. Inner wall is higher than the outer wall. You get on the drawbridge. There's a wall there, like a mini castle. They throw rocks on you. You get past that, you get into the gatehouse. The gatehouse is covered, completely covered except for some holes. They call murder holes. They throw stuff on you. You get past that, past the outer wall, you get into what they call death zone between the walls and then towers and everything. And then, you get past that. That's where the real fight starts. That's where all the soldiers are. So yeah, so what these guys really understood 700 years ago was security in layers. Every step you took towards taking the castle, things just got worse for you. You really weren't any closer to taking the castle. Incidentally, getting into that castle was not the only thing it was good at. It's also really good at keeping people from going out of the castle. I know this because I managed to get locked into Beaumaris Castle after closed for the day. It's an interesting story, and I may tell it one day if I'm drunk. So anyway, I got out. I'm here. So anyway, security in layers. So what's involved really in taking on this sort of problem? Two things. First, you got to define your attack surfaces, and that's it's really kind of a basic thing. everything that connects to the outside world takes network input. That's an attack surface. You have an SSH port open. Well, you know, you've got the SSH. That's an attack surface. There's a buffer overflow in SSH, the SSH daemon, or if there's a weak protocol implemented in it, or even if your SSH implementation is just not up to scratch on the latest broken crypto, or God forbid you run telnet, right? But also things that take network input. For example, the BGP daemon. BGP is relatively complex binary protocol. It doesn't take a lot of imagination to imagine. You see, you can maybe overflow it in some way or another. In fact, there was Quagga had upstream Quagga had a BGP VPN overflow problem, I think, last week. Well, it was patched last week. Anything that takes network input, though, you know, you can get a config file in there and it's got some sort of problem, or it doesn't have a problem. It just happens to open a port somehow. That's an attack surface. Now, the second thing you need to do to get your security in layers is define your proper allowed input-output channels. So, you know, if you have, for example, a CLI, what's the CLI really need in the case of OpenSwitch? Well, it needs standard in, standard out, and it needs a socket to access OVSDB, and that's it. It doesn't need anything else, literally nothing else, no system resources at all, right? You can sum them all up that way. They're not all as simple as CLI. For example, if you have OpenSwitch, OPS switch team. Well, what does that need? Well, obviously also a socket into OVSDB. This is the one thing that, of course, all the daemons have in common. But also it needs a connection to, or a way to connect to the ASIC in the system. Or you know, whatever passes for it, like maybe E4 or something like that. But that's your defined channels. The key is you define your channels for every daemon, or every piece of software, and that's it. That's all that gets through. So how do you do that? Well, technology is to the rescue here. The first thing is process isolation. Process isolation technology has been around. It is quite advanced now in the Linux kernel. You may know it as containers. It really is just process isolation tech and some resource limitations on C groups. So what it really comes down to, the name of the game here is namespaces. There's a few namespaces, a few different namespaces in the Linux kernel. File system namespace, for example. It's like you know, classic way to describe it is a change root on steroids. There's a network namespace. You get your own route tables, your own RTNet link, so policy routing, policies, everything. PID namespace, a few things like that. Those are all really good layers. You know, if you stick your daemon in its own file system namespace and there's nothing there, well, okay, somebody might buffer overflow the daemon, but there's certainly not going to be a password file there at this NIF or a socket to subvert or anything like that. So it's a layer, right? Second thing is reducing privilege. The privilege that your daemon can get up to. Obviously, don't run it as root. This doesn't really need saying in 2016, of course, but not so obviously, run it as a user. That's restricted in all kinds of ways. Throw Linux kernel technology at it to literally keep that user from doing anything. The Linux security modules, there's a few, can really help with that. There's mandatory and discretionary access control, which are really big words for saying permissions. Discretionary access control is just Unix permissions. You have, if you do have, for example, something in the namespace that needs to be open, a socket, for example. Well, you know that socket should, if that socket really only needs to be read by the daemon, all right, then it shouldn't have write permissions on it. Mandatory access control is such things as, for example, AppArmor. AppArmor will let you do things like say, okay, files in that directory and all subdirectories you can only be read or can only be written to by this or that user, or that user can only do such thing. There's a bunch of things you can do in AppArmor. AppArmor is just one example of a Linux security module. Perhaps the more famous one is SC Linux, very widely used as well. Anything else you can find. Anything else you can find in the kernel that will help you. And new stuff like that is developed all the time. In fact, there's four Linux security models now. The fourth one is I forget what it's called. It's sort of limited. It's almost like a proof of concept, but it's pretty new. You know, you could develop your own. It's not even that hard. Stuff like that gets added all the time. The namespaces, there's I think 7. Does anyone know? 6 or 7 namespaces in the kernel right now. If there's room for more, I can almost guarantee there's going to be more. So you throw everything you can at it. That's your layers. That's your security in layers, right? The question, of course, that needs asking is, so when you stop, how far do you go? I mean, when is enough enough? Do you really need to do discretionary access control, Unix permissions, and mandatory access control? Basically the same ACL on the socket or on the file and everything? Yes, you do. You absolutely do, because those are 2 different layers. If there's something wrong with the permissions, with the Unix permissions, or some attacker finds a way to subvert them, then there's the next layer, SC Linux or AppArmor layer, to keep you from going any further, right? So when do you stop? Well, you don't stop. It's turtles all the way down, right? You don't stop. Keep adding layers. All you need to do is make sure that your defined channels keep going, keep working. Right? That's why you need to define them. So, a few pitfalls. When implementing such things, there's no silver bullet. There's no one-size-fits-all solution, something that you can deploy and say, there you go, secure. I'm thinking here specifically about FireJail, which has come up in the OpenSwitch project. FireJail is essentially a wrapper that lets you define a bunch of security technologies to deploy. It has interesting things like seccomp. I think it has, what else? I don't know. You think namespaces as well. You can even restrict the network protocols, things like that. FireJail is not the point. The wrapper is not the point. The point is, what does your daemon need to do? Right? What are the channels that it needs access to? And how are you going to secure them? The wrapper is not the point. You can't just throw one tool at it and say you're secure. I'm a little worried that this is the conclusion that may get drawn from add more security. You need to think about it. It's not so simple. You need to really think about it. Bring me to the next point. You can't have checklists. You can't have something like, okay, we need to deploy. Let's say we make a checklist, and we're going to do Unix permission, and we're going to do AppArmor, and we're going to do seccomp. So 3 checkboxes check, and we're done. Or you're not done. Turkeys are done. Security is never finished. Security is a matter of eternal vigilance. There's always some next attack that comes along. There's always some new technology you can deploy that will keep your attack, this attack from going any further. No checklist. Keep thinking. No exceptions. You can't have somebody saying, yeah, okay, but I really don't want to do access control. I'm just going to make this thing world writable. That way I don't have to think about it because it's really kind of handy. Or something that specifically happened in OpenSwitch. I want to have this CLI secure, but I still also want to jump out of it into Unix shell. Well, yeah, okay, but you can secure your CLI and still have it able to run a complete Unix shell with all the really wild and flexible functionality that it has. You got to choose. And the choice that was made was to remove the functionality of starting a Unix shell from CLI. Be very careful when granting exceptions or bypasses, and go right around your security. And finally, my last point, it's okay to make incremental improvements to your security. You don't need to get it right all at once. You just need to keep improving. If you say, okay, we can't get SecComp done this release, or we can't get it done this month, we still got a roadmap. All right, that's good. As long as you keep improving your security with every release, that is just fine. Avoid the quest for perfection. Right. So with that in mind, what I think needs to happen for OpenSwitch is, well, obviously, I think all my advice should be heeded. That goes without saying. But I think that somebody needs to really take this on as a responsibility. So what I'm going to do is, surprise, I'm going to give you a new hat to wear, Michael. You're now the security czar for OpenSwitch, and you need to keep this in mind as well, because it's very much part of the architecture. I think you need to, well, basically, OpenSwitch is a project that's starting a network operating system basically from scratch, and it's a golden opportunity to get security right. Nobody does it like this. The closest that I've heard is Cisco's iOS XR, I think it is, where you have one VM for the CLI and another for the actual daemons. That's what I'm talking about. I'm talking about Beaumaris Castle. And it's a golden opportunity to make security part of the architecture from the ground up. So that's all I got. Do you have time for questions?
Yeah, we have.
Okay. Any questions at all? Everybody just agrees with me, or what?
So, yeah, actually, I saw some of the discussion, actually, some of the comments I made was that I agree that in particular, I was also concerned with their servable only with Fergel. And actually, someone was asking and saying, well, I think that SA Linux could be a better option in terms of, providing a framework, right? It's still a lot of work to go through, right? And especially just
doing the work is not the problem.
Right.
Incremental improvements.
Right. And I think that approach, like enabling SA Linux in the base, could help us. I honestly don't have the experience with the SA Linux environment to know what's all of it on there. That would be well designed for it. So we actually would design for having mandatory access control, way more than what we have in the Unix permissions. But it seems to me, and maybe someone has experience with how it works in other distributions, because I don't really have that experience.
Well, let me tell you first of all, SE Linux and AppArmor and Yotomo, I think it's called. No, Tomoyo. It's an NTT project, and one other. Those are the 4 Linux security modules. You can only have one. Basically, you choose which one to compile it. I only know AppArmor because it's simple, and I'm a simple man. But SE Linux has the reputation of being hard to deploy and just more work. But I think there's a guy sitting right there, yes, you, that knows SE Linux. Am I right? Yes. And he works for HP, so he's more than happy to help. You are, aren't you? So, but I mean, it's one Linux security module. I think I don't have a preference. I don't know the other. I only know a little bit of AppArmor.
Again, it's not a silver bullet. I'm saying hey, just turn it to Linux. Now it's safe.
No, absolutely not. But it is a matter of let's discuss it. Let's discuss it on mailing list. Let's decide on the Linux security module to use. Start the work.
Right.
What's your opinion on Snappy?
Snappy. Okay, Snappy is a base operating system with pieces you can snap onto it. Right now, we're doing the base operating system in OpenSwitch with Linux. There may be more options to that coming, I think, besides Yocto. But I mean, it's on that level. Security is really not much the point. However, from what I understand, I don't know much about Snappy, but from what I understand, it's basically a framework that uses, among other things, AppArmor for isolation of the different snaps. So it does pretty much limit you to AppArmor, and then obviously you're not going to have an SC Linux deployment on top of Snappy. Oops, power. Yeah, it's kind of a challenge in the sense that since the hackathon a couple of days ago, OpenSwitch in fact runs on Snappy now, and congratulations to the people that did that. If they're here, but that's great. But I mean, that sort of thing is a challenge. If you're going to have an OpenSwitch installation that's not based on basically a totally custom Yocto distribution, but based on, for example, a bare bones Debian or Fedora, then okay, there are going to be some integration issues to consider with this sort of thing, security. That doesn't mean it's impossible. It's just something to take on as part of the integration. So it's not a big deal.
I think there are also different levels of approach that we can use. For example, if you think of something like SL Linux, right? There are some hard points where you have to integrate, like, you know, CLI and some of these surface attack areas that are more carefully where we have to integrate. But there's also things that you mentioned, like channels and capabilities that we can actually handle with something basic as systemd. So actually, systemd has a framework so that you can just in the service file you can drop capabilities from the demos.
That's right.
Right. So it's just capability limitation in the demos could be actually a pretty good improvement already. That is portable across distributions. So that is certainly working very good, right? But it's interesting because
is already pretty much a dependency for OpenSwitch. So
right. Well, it still works. You know, capability limitation is a standard Linux feature for ages. So good work.
Okay, guys, thank you, Bert. That was a really, really interesting presentation. The next one is Parag. Parag is going to talk about what Barefoot is doing in integrating P4 emulation into the system. Let me just open it.
So I'll be talking about what we are planning to add.
Just this microphone should work.
We are planning to add to OpenSwitch. We are going to contribute P4 a simulator that can be used as in a container environment, which is much easier to start developing, add features, and so forth. And I just heard that we have some limitations in terms of what OBS can do and how hard, or it can be hard to add stuff to that. So I think P4 will be really useful to help in adding more features and so forth. So just one quick introduction of what P4 is, and I think everybody knows, but basically P4 is a language that was designed to define how packets are processed in the pipeline. You can choose what packet speed to look at, what headers to add, remove, and what to do with those, what lookups to perform, and how to direct packets to different ports and tunneling and so forth. So P4 is a language to do that. So once you understand P4, and it's a high-level language, so it's much easier to define your pipeline using P4. And once you have that, you can then take existing pipeline that's defined in P4, add features to that, or improve some existing features, or tweak some features to suit your needs, or all things are possible with a P4 defined pipeline. This is a good prototyping and testing tool because with the simulator that we provide, it can run in the container, so you don't need real hardware. You can basically take it and spin up a Docker image with that P4 switch, and you can start prototyping things. And again, Michael was saying, let's say today it is OBS is being used for the same thing, but if you want to change something or add something, you have to go modify OBS, understand how it works. Instead, this will be writing a P4 program, and then we provide all the tools to convert that program and run it on the simulator, and then you can basically add your features and test them. And then that means you don't have to wait for any hardware vendor to provide the features that you need, but you have everything that you need. Now, other thing we wanted to do was just providing a simulator is not good enough because you need to have something interesting that you can simulate with it. So instead of providing just the behavior model that executes P4 program, we also are going to contribute what we call switch.p4, which is basically a good starting point because this is a P4 program that we have written, which has a lot of data center features that we think are needed. And again, it's being modified every day. We are adding features every day and so forth. And this would be also checked in along with the simulator to OpenSwitch. And this is the one that we are going to use to start replacing OBS with. And and then other thing that we want to try is whatever plugin that we develop using this. Once you have, let's say, P4 capable hardware or devices, you should be able to compile same P4 program to that hardware and also use the same plugin as much as possible to run your hardware. So there are three components that we are going to add. One is, and these are the names that will appear in the OpenSwitch repository. One is ops P4DP, which is really the simulator of the data plane, or also called behavior model. The second component is a P4C, which is really a P4C compiler, which is used to compile the P4 program and make it available to the model so that model can execute that program. And the third thing is obviously the plugin or the glue logic that connects switch daemon to our simulator of the ASIC. And basically that is used to do the runtime configuration, statistics, and whatnot. So I'll explain how these three components get together. So the simple way, like any other C program, for example, right? So you have a P4 program, you have a P4 compiler, and when you compile that program now, compiler will have different backends. The backend that we are checking in is a backend for the specific P4 scenario. But when you have P4 device, you will have a device-specific compiler, which will generate whatever the device needs in terms of understanding that P4 program to execute. So the current compiler basically generates a JSON file that converts all the P4 definition into something that our model understands. And once that JSON file is provided to the model, and then as the packets go through the model, it looks at the JSON and it figures out what it needs to do with the packet and does all the transformations on that packet. The model that we are going to contribute basically right now has 64 ports enabled, but it can go up to 256 ports very easily. And there are some number of front panel ports and one CPU interface, and that's how it's modeled right now. And all the traffic basically that goes from all the control plane protocol traffic that goes from front panel port to CPU daemon, LLDP daemon, or BGP or anything, that will go to CPU interface, and I'll show you how that gets demuxed into kernel interfaces later. So there is one side or byproduct that we generate as a compilation process is what we call program-dependent API. Because you would be defining all kinds of tables and lookups, TCAMs, hash, whatever. Based on what you do, the compiler will generate C code that you can use it as a library to access those tables a little bit easily. As in, you can have functions that will say, create entry or delete entry or modify entry and those kind of stuff. So it makes it a little bit easier. You don't have to use it, but that makes it a little bit easier to use. So how this fits into OpenSwitch architecture? So obviously we have the OVSDB server and the switch D. That's where at the bottom side of the switch D is where the plugin comes in. And we have two components there. The PD API is the one that I just showed you, which is generated by the compiler. And then there is one API on top of that, what we call switch API, which is handwritten and which is a higher level abstraction as compared to what PD API is. So for example, PD API, let's say you have two tables, a SMAC table and a DMAC table, then you will have PD APIs to manipulate those two. But if you go to switch API, then you will say add a MAC to the MAC table and it will take care of adding it to both. Or if you're doing add route and if route happens to be, it'll add the route and it will put next stops. If it happens to be ECMP, it'll program the ECMP table and so forth. So that's the level of abstraction that a switch API provides. And with the isolation that came in with the emulation namespace and the switch namespace, basically we run the simulator in a separate namespace, which is emulation namespace. So all the protocol daemons and system that's running in switching namespace doesn't really have direct access to the front panel ports. I mean, it'll access them only through the interfaces that are created in the SWNS namespace. And that is the job that our plugin does as part of processing the packets. So what plugin does is all the packets going which are CPU bound or coming from CPU, they come through the CPU interface, and then plugin figures out which actual terminal port it came in on, and based on that it will re-inject the packet into the kernel interface. But that way, the protocols that are receiving packets, they really don't know what's happening underneath. And then, like I mentioned, the JSON file that we compile, that goes on the image, and that sits with the simulator.
So the switch.p4 you said, that's a bunch of programs here?
Yeah, so switch.p4, I mean, we call it one file, but it includes a bunch of other P4 files. But overall, it's one program that defines the complete parsing, deparsing, and all the lookup that happens.
So you will use a read between this to emulate the front panel ports to the applications?
Yes, so that is the CPU interface is a read, right?
Not only CPU, the front panel, if you're running a different namespace, so how are the interfaces visible to the application?
So these front panel ports, port 0 to N, these are really what we create through Mininet. So let's say you do Mininet admin, that's the read that Mininet creates for you, which connects your host to your Docker namespace. And then we create other tap interfaces, which are interface 1 to N.
So there will be tap interfaces at the CPU.
Yeah, those are right up here.
Those are tap interfaces?
Yeah, those are tap interfaces.
So this basically acts as augmenting the OpenSwitch, so whatever is not.
No. So once you have this, you would not be running OpenSwitch in the system at all.
Yeah, so we previously used OpenSwitch. We got all the limitations, and this is much better.
Maybe clarify how the OpenSwitch derived components are similar, right?
Yeah, absolutely. So, when we use OpenSwitch server, obviously, beautiful server, it's just that in the virtual image, if you go today into virtual image and you look into it, you'll actually see two OpenSwitch servers. One of them is the OpenSwitch server that we run, that's our main part of the system. And then there's another one because it's just OpenSwitch. So in the physical machine, you will not see it. Physical machine, there's no OpenSwitch. There are some components that are using protocol based, but there's no OpenSwitch. In the Docker container, you see OpenSwitch and OpenSwitch. Using it to do all the packet handling inside the container. Now we're going to switch into this simulation. So OpenSwitch is going to go away from inside the containers. The obviously server, all this stuff will stay, but the OpenSwitch itself will go away and will be replaced by this.
And does it also emulate performance, or is it just functionality?
So this is a software model, so obviously it's not going to be at anywhere close to line. It's functional.
Yeah. In general, we're not putting any objective to have to create a software switch. Right? So OpenSwitch is not supposed to become new virtual switch for any environment. I hear crazy ideas in the community about actually taking it there. Right? And maybe people will do it. right? But in general, this was not the objective, and this is not the objective that you're taking this way, right? It's more for the development, for testing, for scalable testing, right? So this is why we need the software models. Very. So you know what Diego was showing is the visual when people drop into virtual machines. It will get exactly the same thing, right? Docker container or VM, it's all the same. We'll run it.
How big the size?
What's that?
Or what is the size of
The P4 program or
the whole simulator?
In number of bytes?
Bytes.
I don't know how to say.
So it's a smaller, you know.
Yeah, it's just one executable.
Yeah, it's pretty small.
Yeah.
I can run multiple.
Oh yeah. Actually, if you go to our demo booth, I'm running 2 images or 2 Docker containers in 1 minute topology, and that doesn't even do anything to the system.
Right tension.
Yeah. So basically, this is just when we have P4 capable devices, the transition. What we see is the way we have written the plugin, because we have the switch API abstraction and the program dependent APIs are generated by the compiler. So even if you change your target, as long as your compiler can handle your backend target, the plugin should be just the same, and it will work. It will work with your hardware as well. So one note is the switch.people, like I mentioned, it has a lot of features, that are implemented. For example, it has VXLAN, it has mirroring, it has a whole bunch of other things. But our current contribution is focused only on L2, L3, and as that goes in, gets merged into master, we'll start adding more features with HP and with.
Okay. So the plan is that Barefoot right now contributes to catch up on the existing features. And then existing teams, existing people, whoever is working on specific features, they will have to actually integrate this before they should run. And they will test it first, right? So they will do all the platform dependent work and before piece, so they can test everything. And then other plugins that will actually come up to speed and will implement the same things and be part of the platforms. And then we can go there.
That's pretty much it. I mean, we have a demo running where what we are showing is we are showing 2 containers talking to each other, BGP and lag and all those things. But we also have HP switch, which is real switch, and we have connectivity between container and the real switch, and we can actually show that there's an end-to-end traffic that goes between those 2 also. So it's fairly interoperable. And then these are the places. So whatever code that we have open sourced it at P4Line, which is our repository. So from OpenSwitch, we are just basically pointing to our code base, which is there, and it's all open source.
All Apache devices?
Yeah. Any questions?
Any questions?
So switching to is it like OpenSwitch or it will be traditional like learning if we try and all those things will do together in that?
So that is how you write your P4 basically. So your P4 program will decide what your switch does. The switch.p4, like what I said, it's a L2, L3, so it will do L2 learning, it will do routes and all that stuff. But
not a typical flow-based.
No, that's not our switch.p4. But if somebody wants to do flow-based, they can write another P4 program and it will
do. The trial covering that may have increased to be created if it is into learning the learning.
Yes.
Flow versus like.
Yeah, that's right. So right now, in fact, we are doing Mac learning and aging within our plugin itself, but we'll integrate with whatever plans you have.
Just on OpenFlow, right now, Broadcom, for example, is implementing OpenFlow API. OpenFlow APIs exist inside OpenSwitch because we're getting it from OBS. So Broadcom is now implementing OpenFlow APIs in OpenSL plugin. Right? I can definitely see how we get this implemented inside P4 plugin. For them to support, we have to improve switch.before program itself. Support what we need. And so we can get it forward, and obviously there will be people who will be interested, and we will get it done. Yeah. Okay, last question.
How can I build this?
So this will be is the same Yocto build process that that we have. So when you do make for, and the what do you call, architecture is x86. So when you build x86 64 image, I think there is one small file that you need to modify where you say target is P4 versus container.
Okay. Do you have any? Can you share that after?
Oh yeah, absolutely.
Thank you.
We're still working.
Although the code is not merged into master, so you will not see the code.
We're still working and change that probably tomorrow we'll finish up in the conference. We'll start working on it today, but.
Tomorrow?
Yeah.
Great. That's what I want.
So eventually when we just switch over from ODS to P4, it's just going to be default. You will not have to modify files.
Right.
We only say the same to our clients and go.
But until we catch up, you have to specifically go to P4 to do that.
Thank you.
Thank you.
Okay. Thanks, Brian. So, Ali. I will take that one.
Hi, good evening, everybody. I'm Alex Fishman from KVM Explain. Thanks for coming and staying for the late hours. I hope you didn't come only because of pizza, but because of your interest in OpenSwitch and other things here. Yeah. And also thanks to HQ for hosting this event and to Devasis for organizing it. So I'm representing a KVM Explain, and I will talk about our switch, flexibility of our switch, things it can do. And also we are now officially part of OpenSwitch. We opened up our upper layer of APIs, similar to OpenNSL. We call it OpenXPS. We contributed our repo plugin to OpenSwitch. And if you go to a ONS Summit, you can actually see demos that we have a couple of boxes that they run in OpenSwitch and can do good things. So our switch, this is our switch. This small thing can do 3.2 terabit per second of throughput. We support ports, all these combinations. We can do 1 gig all the way to 100 gig, 10 gig, 25, 40, 50 gig. The main thing is the chip is this software-defined engine. So our chip, I believe, is truly software-definable chip in terms of, unlike maybe traditional devices, that the traditional device just can support certain functionality and just tell software, this is what I can do, take it or leave it. In our case, software can truly go and define the functions of the device. And when I say the software can truly define, truly define what it expects from a device, it's in sense of the pipeline, as well as all the resources. These resources can be associated for a specific deployment cases. So we integrate, as I mentioned, 128 services, 25 gig. We have 24 megabyte fully shared packet memory. It means that we don't have like internal cores or whatever. So this is truly shareable among all the ports that we have. We have 14 megabytes of programmable SRAM that software can define to access this SRAM for which feature to use this SRAM. Software can define the key to access the SRAM, the type of table. It can be hash, it can be direct access, it can be LPM for routing purposes, as well as the action that is derived from the search. We have also 3 megabit of TCAP and integrated traffic manager.
So it can work on any arbitrary bit pattern, is that what
Yes, so we are integrating actually a programmable parser. So you can, in that parser, you can program the header types that you want to support, and we will be able to parse these headers and process based on the parsed headers. That's why for us it's very easy to support our various tunnels, so we easily support, VIX, LAN, GNIB, including processing on the GNIB options, a GRE, and whatever will come. For us, it's kind of natural to support all these things.
Is there a limitation on like number of lookups or the number of bits you look at to meet line rate or?
So I think that's something that can be discussed separately, right? I don't want to go to our specs in this forum, but on general note, we are very flexible, so we can process this as 3.2 tera that I mentioned before. In terms of parsing, we can do up to 192 bytes of the header, which is enough. And you can parse every layer, and the parsing happens. We do offset to where the layer starts, so you can actually parse any type of a header or protocol.
Yeah, that's the answer I was looking for.
The whole pipeline is made like that you cannot it's old because there's monitoring from getting the memory and so that is taken care of to support these performance. So there's block in the starting.
Thanks, Divash. So actually, if you take one of the problems with the traditional ASICs is this very, very long cycle of new development. So let's say that there's a new protocol comes up or a new requirement. So in most of the cases, the ASIC will not be able to accommodate these requirements to require a tape out. And typically, this process takes this is typical cycles for ASIC. It's like 30 months from the moment that your definition starts and architecture and design and layout and all these things. So in our case, because the chip is actually software definable and the hardware architecture is just a bunch of these engines and TCAM and SRAM resources. So for us to accommodate all these requirements, it's something that we do within months, and practically for important customers, we do it even much, much quicker. It's just software code change. So all this programmability and flexibility allows actually using same hardware, same chip, and same software. When I say same software, it can be on SDK level or it can be at the operation system level for completely different deployments. So for example, we can optimize our chip for route-centric pipeline, which means that the pipeline itself, the functions of the pipeline, they optimize for routing purposes. And in this type of deployment, in this type of configuration, we can support more than a million routing prefixes on the single chip without going to external memories. You can reuse exactly same chip, again, same software, same hardware for OpenFlow pipeline. And also here, we can do pure OpenFlow when all the resources are actually optimized for to be controlled by OpenFlow control plane. Or we can do hybrid mode, where we support both the traditional pipeline as well as OpenFlow. So for example, software can define certain criteria based on which certain flows will go through the OpenFlow pipeline. You will modify them, you will re-inject them. Either you can send them out directly, or you can re-inject, let's say you can manipulate IP and re-inject them back to the normal pipeline and perform the regular route lookups. Same chip, we can do also all kind of data center profiles. We call this personalities profiles. We can optimize for a top of the rack type of a chip. We can optimize for spine. Each one has different characteristics in terms of functionality as well as in terms of scalability of certain memories. And all these things, so you are getting many chips actually in one chip with the same software envelope. Sure.
So
when you have all these multiple personalities, how does the software on top adapt to all of this?
So I can take it on this one.
Which software? Any control platform.
Yeah. So right now, and that's what the Kevin is showing in the booth at ONS, we're going to have inside K-config system that we're putting on top of Yocto, right? We're going to have basically under Kavio, we kind of multiple ASICs, right? So it will say, okay, we have ASIC which is layer 2 or ASIC with layer 3, whatever they define, whatever pipeline they define, and do multiple ASICs. And based on the pipeline that you choose, based on the ASIC that you choose, it will actually disable some of the features or enable some of the features. In the future, hopefully, we'll get to extend K-config system to the level that we can actually choose the scale, not just the features. So now you will build layer 3, layer 2 image, Qualia will go away, and all the routing will go away, CMP is going to go away, you get the image which only has layer 2, but probably has many adjustments, or something like that. And so yes, we'll get all this integrated, so all these flexibilities have to boil up into the software that it should be effective. I don't want to see CLIs for routing if the ASIC doesn't support routing.
Yeah, thanks, Michael. So on top of his answer, so it depends on the software that actually controls the device. So in case of the OpenFlow, we have this tight integration between our SDK and software. So obviously the daemons will be aware of our scalability numbers, functions available, all these kind of things. We can configure through maybe other mechanisms because of this tight integration. For example, if we use the OpenFlow, there's this table feature through which we can say how many tables we support and which actions, which flows we support. So it's exposing is one thing, but I think that the main point, the main message that I want to convey here is that in the same ASIC, you can actually optimize it for a completely different place in network, and it will work. So it's this slide. Actually, I brought it in to emphasize that for us, for Cardinal, for Xpline, this open source and ecosystem. That's something that it became part of our DNA. We see it as something very important. So you can see that we support in the all main open software stacks available wherever it makes sense from the business perspective. So our XDK runs with, just to name, with all these OpenFlow controllers, with Airbus, which is a Facebook operation system, Airbus agent, obviously with the OpenSwitch and with PKA. We support also SAI, all these things. But again, I think that OpenSwitch is evolving to the main open source networking operation system. So we are in Kavio, we see it as a strategic investment for us. And I think I have it in the next slide, but we are aligned to the feature set of OpenSwitch, and going forward, we'll stay aligned, and probably we will contribute features and we'll move ahead of the official release feature set. So a couple of releases that we did as part of. I didn't expect you to read that one, but just to mention.
Just to see the fullness.
I had to fill the slide in, right? I couldn't place it horizontal, vertical. So the thing is that a couple of things that we did to support OpenSwitch. So one thing that we did, we have opened our upper layer of APIs. We call it OpenXPS, which is the Open Xpline Switch APIs, or it's a Open APIs for programming Xpline Switch. It is the same concept as OpenNSL. I think that I'm not sure what the Broadcom plans, but I can share our plans that we plan to open. I think everything. We don't see any keeping APIs to ourselves as some kind of intellectual property. So we are going to open all our APIs and all our features. So this is open. Thank you. This is a OpenXPS. And also for the OpenSwitch, we also contributed our code to the repo. It's available.
So how the APIs work, as somebody was asking, if I change the personality, do you have a mechanism to auto-generate the APIs or?
So the personality actually has nothing to do with APIs. APIs is how you control the switch, and in terms of personality, what happens is something that we do in build time, pre-compile time. So we have our language, we call it XPC, which is explained C, something very close to C. And you express that functionality, describe all these engines that are available, which function each engine performs, what kind of lookups that engine executes, and what decisions it applies to the bucket, and what kind of metadata it passes. Then we compile this code, and the result of that compilation is actually registers configuration that at any time RSDK takes care, and through PCIe configures the device. There is no microcode or stuff like that. So we pre-configure the device at any time.
But the upper layer APIs are constant.
Upper layers API are constant. Yeah. So again, if certain features are disabled, then I don't know, it may not be operational, but they're still available.
So from kconfig perspective, what will happen is once the features are chosen, the information about which features are enabled and disabled is all boiling down to every repo. So, and then if it will they will get inside the plugin, inside the Kavin plugin, Open XPS plugin, you will get information about which features are enabled and disabled at the build time. So they will be able to actually disable some of the features inside the plugin, say, okay, this one they're not calling, this one they actually calling, and stuff like that.
So that's the Open XPS GitHub. You can go. You're welcome actually to go, and we are tracking statistics. So if you clone, you'll know. No, actually we don't know the names, but we know how many clones happen. So if you go to github.com/explain/openxps, you'll see we put there all our APIs and also binary of our SDK. So you can just download them. Apparently, if you have a box, you can run and see what happens. It will work. That's our contribution to the OpenSwitch. Also, the repo is available. So now a couple of words how we exactly integrated OpenSwitch with actually our XDK with the OpenSwitch. So that the OpenSwitch architecture diagrams that I think Michael was showing before. So what we did, we added our plugin here in that level that talks to OPS switch D. Underneath, we are using this XPS APIs. And underneath, there is Explained XDK. So again, if you go to that OpenXPS, there is a compiled binary image of our SDK. If you have an NDA with us, then obviously we'll share with you the sources. And we also have the drivers and the kernel models that we provide. So all these things, they are real. If you go actually to NS boot, if you go to Kavin boot, you have also Kavin boot, and as well as I'm sitting and OpenSwitch boot, you'll see that we are running actually demo with OpenSwitch. It's a real hardware. In this case, we are using a Acton hardware that is it's an OCP platform designed that we contributed to OCP. And we run OpenSwitch image there. Just one thing to mention that we took advantage of the flexibility of our device. In this particular case, we configured the routing kind of capabilities, and we pushed more than 1 million flows, 1.2 million flows to that device without any external memories.
You mean rows?
Yeah, prefixes. Yeah, okay, let's say almost the end. So I mentioned before that we can do different personalities to our device. and you've asked how these personalities are exposed to OpenSwitch. So in this case, we are using kconfig. And if you go to kconfig, you can configure, platform-specific configurations, daemon features, as well as the ASIC-specific features. So you can see that we have, for example, these profiles that can be configured through kconfig and OpenSwitch.
Just to note, this is demo, right? So we mostly didn't do this kind of mockups for the demo to understand how we should look like for kconfig. The kconfig work is now undergoing, but people working on integrating kconfig. So when you do make menu config today, you will not see it, but it will happen once kconfig is in. Then Kevin will go this way.
Yeah, and on our side, all these profiles, they're real profiles. So we do have these profiles. And once the infrastructure on the OpenSwitch side will be available, we will populate and we'll load for each of these profiles. We have a precompiled, this init files. So when the OpenSwitch infrastructure is ready, we'll select the right file. But on the hardware level and on the SDK level, it's this thing is real. Okay, so we have just a couple of minutes, but we have a demo running in ONS. So what we did, we took this standard data center topology, and we represented it using four switches. Two switches are play a role of spine devices, and two switches are playing a role of top of the rack devices. We also connect them. That's not real, but not happen typically in typical data center. But we connected this top of the rack boxes, the lab, just to show that we can do layer 2 lab. And we are running various use case scenarios that are showing ECMP. The packet can go this way, or the packet can go this way. And we can do also a layer 2 functionality. All these things are available using real hardware and real OpenSwitch image taken from the open source. That's not the presentation that I sent you, but I had also one final slide that, today I saw in the ONS there kind of statement that open software opens a new era. So I believe that, this combination of truly software definable and programmable ASIC and modern, advanced, and flexible open source operation system, that's a very powerful pair. Questions?
I have a question. Regarding the OpenSwitch, do we use DPTK technology here? Or?
No. Not on our side. No.
The question was, do we use DPTK technology? This is not, so OpenSwitch is, first of all, is not software switch. This is for the hardware platforms. So the data path is inside the ASIC.
Okay, so the 1 million route will be pushing both the kernel side and the ASIC side, right?
Yeah, so our chip is capable of keeping this over 1 million routes.
Yeah, but my question is the 1 million route, I think is too much for the kernel side, right?
So it's like you need to push stuff into the kernel because the slow pass is inside the kernel. So did you push the routes inside the kernel the same? So did you let?
So for this particular case, because OpenSwitch is still something in the involvement for pushing over 1 million routes, it's something that we push directly to our SDK. However, all other use cases that I was showing here, all this BGP conversions and everything, this thing goes through OpenSwitch and kernel and everything.
But the question is good because kernel has to receive all routes. And because whenever you have miss, you have to actually send the packet to up and let it resolve to ups and everything, and then go to slow pass to up.
Yeah, because the protocol is running on top of the kernel, right?
Because the slow pass is on the kernel.
Yeah, right. Like the BGP, like
no, not BGP, but the actual routes, right? The
individual
packets then they don't have the next one, right? They have to go up, and then there will be resolution, and then they go up. So this goes as well.
Okay, thank you.
But in the kernel, having that in the kernel is just a matter of memory. There's nothing magic about it. Having a million prefixes in the ASIC, that's amazing.
Yeah. Without external memories.
Yeah.
Yeah, that's true.
I guess last question maybe to Alex.
Can you please spell a few words about the combination of, let's say, Cavium, programmable ASIC, OpenSwitch, and P4? How P4 fits into this story?
So, let me start with the first part of the question, and then I'll get to P4. So, as I said, our chip is very unique in terms of, it's a hardware chip that is available, and I believe it's the only SDN chip available today. So we can do many, many things, and since OpenSwitch is an operation system being, written now, and we can expose all the functions, and we work pretty closely with them, I believe that this operation system will be able to take advantage of the programmability and flexibility and come with features that the market expects. Now, in respect to P4, our device currently on the software level, we do not support P4 just because P4 is a way to compile your pipeline. So we do it using our own explained C language. That's the other way. And I think that the final goal is to allow the software to compile the pipeline that we want. It's less important what the way to do it. And currently P4 is more of a barefoot thing, but if there's a market requirement for P4, on the technical level, for us, there are no issue to map P4 instructions into our device architecture and capability.
So from OpenSwitch perspective, right now we just support different drivers, different plugins, right? So OpenSL, SAI, OpenXPS, P4. If ever the Cavium decides to actually go under P4, then you can just go to P4 to Cavium. But that's up to them to actually decide. Right? We are not getting into the wars of who defines which APIs. Right? We can support all of them. So right now it's just different concurrencies. You can go with, if you want to run ASICs from Cavium, you use OpenXPS plugin. If you want to run inside container, inside VM, you use P4 plugin. Eventually, when there will be P4-based ASICs, this plugin will actually get you on top of P4 ASICs.
When you support SAI, why you want OpenXPS? When you support SAI, why you need another one, OpenXPS?
So I'll say that in this particular case, this tight integration directly between XDK and the operation system is much better than going through limitations of an interface being defined. But we do support SAI. Actually, in OCP last week, Microsoft, they were running their Sonic operation system through SAI managing our device. So we do support, just in this particular case, we integrated directly, and that's the way to expose more features.
In general, if you think about SAI, you will see that it sometimes it plays as the least common denominator for the ASICs, and when some ASICs they have extra functionality they want to expose, then SAI might limit them, and that's the reason why I think Cavium chose to actually go directly to the SDK, so they're not limited by.
Yes, saying that, if you have something external that you want to access our device through SAI adapter is available. I saw that they actually, Mellanox, I think attributed like last week. So we can check if we can connect it to our device, and because we do support it, just a matter of connectivity.
Okay, guys, I think we need to go to the next one, so we the time.
Thank you.
So Jorge is going to talk about OBSDB improvements, performance and scale.
Okay, hello. My name is Jorge Salma. Currently, I'm leading a team working with OBSDB. It actually started with basically a question for the community at that time, which basically was all HPE people. And we asked them, okay, so since you are already working with OBSDB, how it can be improved, right? what do you need? I mean, what do you think about OVLDB? Because at the time we didn't know anything about it, right? Just it was part of the OVS project, and we basically didn't know anything about it. So we got a lot of feedback, right? A lot of requests, a lot of questions, a lot of discussions. So we saw that we should form a team to work on this, right? Because it wasn't so. Some of the improvements that I'm going to talk about in just a minute, they are kind of maybe not a large deployment, but it will take some people to do it, right? So one of the first things is that why we will need to change OVLDB. And basically OpenSwitch has some special needs, right? Derived mostly from interaction with the hardware. We are talking about real devices here connected to the network. We are not talking about virtual environments, right? So OVLDB was designed for virtual environments. So we thought that we might need to tweak it a little bit, right, to adapt it to a hardware environment. And also performance and scale was the main driver. That's critical, right, in switches and network devices. So we did a kind of initial analysis of OVLDB, how it works. And as I said, we found some improvement that could be added to the OVS. Actually, we found a lot, but we decided to reduce the list of improvements to 8 or 9 improvements. So that's what we are currently working on these improvements. I'm going to talk about them, right? So as I said, most of these improvements are related with performance and scale, but some of them are also related with making the life easier for the developers. You will see why I'm talking about this. So let's jump to the improvements. The first one is the first thing that we did with OVLDB is we did a profiling of the module, right? So we found that memory allocation is used extensively in OVS, depending on the operation, inserts or updates or the POP-sub module. The memory allocation could reach hundreds, even hundreds of thousands of calls, right? So it's pretty intensive. So we thought, what if we change it? What if we try a different memory allocator? Because currently OVS is using glibc malloc. So we thought, what will happen if we use tc malloc, or if we use gmalloc, right? So we select gmalloc because it usually uses less memory and it's faster than glibc allocating memory. So what were the results? Actually, pretty good. Using gmalloc, we can achieve 20% and 30% improvement. So we got more responses per second, right, just with this chain, because memory allocation is faster. Of course, there is a price we need to pay, which is gmalloc takes more memory than regular malloc, but it's much faster. And actually, we already upstreamed this improvement to the OVS community, and some people already test this improvement inside their systems, and they found the same results, around 30% improvement. So I think that's the kind of results we are looking with improvements, right? Performance and scale. Okay. Second improvement is well, it is called, it's a big name, but it's called on-demand fetching of non-monitored data for the CIDL. Well, this is in a nutshell is I'm not sure if you are familiar with the OVLDB, how it works, but the CIDL is basically interface between the OVLDB server and the daemon, that it's a replica of the database to reduce the number of transactions going to the database, right? So this replica, it's a pretty good idea, right? But if the database is too big, this replica could grow a lot. So if there are, I don't know, for example, the REST, the web interface, the CLI, they have a replica of the full database because they need access to all the information inside the database. So this replica could grow a lot. So for some specific kind of data, right? For example, read-only data that is seldom request. I don't know, maybe a counter or some statistic or something like that. We created a mechanism that the data is not updated automatically in the replica. So only when specifically the daemon requests this data, the data will be pushed to the replica, right? So instead of having the database replicating the data every time it changes, was just when the client needs the data, it will be updated in the replica, right? So it's it will save us a lot of memory, I would say. Okay. The next one is this is one of the improvement that will be make the life easier for developers, and it actually is something it was kind of obvious to do, right? Because the OBS DB it has special columns called map columns where you can define a key value list of data, right? So currently you will need to retrieve all the keys and values, change the one that you are interested in updating or deleting or whatever, and then update the whole map column, right, with all the values again. So with this improvement, we are allowing the developers to just update the key value that they are interested on. Instead of retrieving the whole content of the map column, it will just say, okay, I need to update this key with this value, and that's it, right? So, and actually, this is already defined on the OVLDB RFC. It is called a mutate operation, but wasn't implemented on the CIDL. So what we did is basically implement the mutate operation inside the CIDL. Okay. The next improvement is when things gets interesting. There was a very specific request from some teams that they will need two things basically. One way to do faster lookups. For example, if you have a lot of routes, I don't know, and you need to find a specific route. With OVLDB, you will need to traverse the whole database, right? All the rows to find the value. But with this improvement, you just can go directly to the route, let's say, to the value you are interested in. And also, there was a different or another requirement, which is the ability to retrieve data in lexicographic order, right? For example, IP addresses or alphabetical order or something like that. So OVLDB is not able to do that. You will need to retrieve all data and then sort it or use a cache or something like that to implement this thing. So we decided to improve the CIDL with providing a data structure that can be used for these two goals, to have faster lookups and to sort data in lexicographical order. Okay, we use a skip list because it was, for us, it was the best data structure for meeting both requirements. All the improvement that I thought at this time, they are already upstream to the OBS community. So we are expecting feedback. We are waiting for their opinion on these improvements.
Is there any improvement results as you shared the first one?
Any improvements? Or?
What is the expected improvements of these changes?
In numbers? This one is hard to measure because currently for the fast lookup, it depends on the amount of information, right? For example, if you have just a few routes, probably searching with the regular database would be better. But after, I don't know the exact number, but after a lot of information, you will get better results with this improvement, right? So I will say that this is not for every table, right? Because it takes memory, right, to keep this data structure in memory. So you need to try. You need to test if this is for your specific case. For example, for routes, what else? That's maybe the main use case, but I'm sure that
currently in REST,
REST
is quite ideal. If you look at the URIs in REST, we use the indexes. For example, if it's a bridge, the URI is REST v1 system / bridges / bridge normal. So this index is basically the name of the bridge that's in the database. And then what we do is we take this index bridge normal and then we search in the entire table to see which particular entry in that table is actually bridge normal. But bridge only, currently we have only one bridge, it doesn't matter. But if we have hundreds of entries in the same table, you'll have to keep looking through the entire table to see what exactly that is. And if you have compound indexes where you have more than one index, then you're basically searching in two different columns in every row. But if you have a map like this, it's a one-to-one operation. So it just makes it a lot faster. So it depends on the use case. For us, it definitely helps us because we are providing data for every table, statistics, and stats columns for every table. So
yeah, actually that's a good point because the indexes can be compound indexes using two or columns. Okay. Yeah.
So for these kind of optimizations, are you creating reorganized shadow copy of the data in memory, which means memory mirrors is going up?
No, we are just this is a parallel structure that is completely separated from the CIDL from the replica. So we are not touching that. I mean, if you want to use the index, you need to specifically create one and use different set of functions to access the data structure.
Just maybe a list of pointers to the.
Yeah, this is yes. It's not. It doesn't duplicate the data because it will be used. We are creating pointers to the actual data.
And that's why they're saying you can enable selectively. Whenever you actually connect to data, you can say, okay, this table says 1 to have it, but this says 100.
Okay, let's keep moving. The next one is we call priority sockets. It's a mechanism to assign different priorities to different processes, right? The main use case is, for example, people will worry about, for example, MSTP or BFD or UDLD or any other protocol that's very time sensitive. What will happen if a transaction related to these protocols will need to compete with a transaction coming from the, I don't know, the CLI for a short version or something like that. So it's not fair, right? It's not a good scenario, right? So we are trying to give higher priorities to some specific processes, right? For example, let's take BLD or Spanning Tree. Requests or transactions coming from that process will have higher priority than the CLI or the web or any non-critical process, okay? We are still creating a proof of concept for this improvement because we don't want to, we are creating proof of concept and measuring the improvement because we don't want to invest time or resources in something that will not give us a good performance gain, right? So it doesn't make sense. Okay. The next one is called the publisher model, which is currently the OVSDB managed, or it has something called a subscription model, where a process subscribes to a specific column or cell, and whenever this cell is updated, the process will get a notification saying, hey, something changed, so let's, since you are interested in this data, so inform that something changed, right? So we're creating a different mechanism which inform a process that this process will need to update data, right? For example, let's say that a process owns, I don't know, packets in or packets out, a counter. So when the CLI or the web requests, hey, give me the number of packets, basically reads cell in the database, the OVSDB, the server, will notify the counters process or the process in charge of returning these counters and say, hey, someone needs this information, so please update it. Okay, so that's the publisher model. This is very, very useful for data that changes very often, but it's not accessed so often, right? Counters is the best example. Okay, and also this next improvement is called OVSDB replication. Useful for high availability, which is basically to make the one OVSDB to work as a client of a different OVSDB. Okay, so if you want to have, let's say, two devices synchronize or replicate the database from one device to the other, you can use this improvement. And actually, the OVS community is currently talking about HA for OVN, one of their products. So I think this improvement could help them. We are about to upstream this change, I think this week or next week. So let's see what will be the response from the community. But that's basically the goal, to have two OVSDB to database synchronize.
So you can see, when we talk about good citizenship, that's exactly what we get. That's the upstreaming of changes, improvements, data communities.
And this last one is an example that is not all reviews. Actually, this when we did the profiling of the OVSDB, we found that a lot of time was spent in the JSON marshalling and demarshalling. So we thought if we use binary objects, we can save a lot of time because this marshalling and demarshalling will not happen, right? But the POC didn't yield expected results. Actually, it was the same time, so we don't know why. But we are going to do a second round of profiling with this change. So to find out why what we saved with the marshalling, we are losing somewhere else. The performance is the same. So
and you did this in CIDO?
Sorry?
Was this done in CIDO? Or?
Yeah, CIDO, yes. So We don't know, but that's part of the process, right? To investigate, analyze, create a proof of concepts, and when we are successful, upstream to the OVS community. So, that's it.
We have one model to do about Ansible. I really want to get it because it's starting getting late and people to go home at some point. So, Kate, you're going to share from your laptop? Okay.
Always this is a challenge. Really. Do I need to connect this?
Yeah, we can see it.
All right. So this is my son. Okay. All right. So my name is Kei Noguchi. Today, oh yeah, and I'm here, HPE now, and I'm gonna have this T-shirt. Well, officially. Yeah, I'm all here. All right. That's right. All right. Today I'm gonna talk about Ansible plus OPS and on Docker. As we know, those hardware chips, that's the goal, but having Docker on especially my laptop is really fun. So I'm going to share that. And also I'm going to share something about Travis CI. So this is really magically and
what is that language?
Happy. So before going to that, I'm gonna play one. So this is my favorite file. Actually, I'm on the so I'm gonna play one play. So by the way, how many of you knows about Ansible or play with Ansible? So what I'm going to do is I wrote a couple of playbooks today, and I'm going to show you how that's so excited, and I'm so honored to be here in front of those magical people. But let's see. All right, so I'm going to show those details, and hopefully that's going to run. That looks like it. All right. So what I'm having today is I have MacBook with Vagrant and obviously Ansible installed, and running VirtualBox with Ubuntu, and I discovered this Docker container Compose is really awesome. So I installed that yesterday and run 6 Docker containers. Obviously, that's OpenSwitch. But, you know, we are here talking about data centers, and having just Docker, 6 Dockers is not that fun. So, can you see it? So I wrote a ASCII diagram to create this topology on my laptop, and the script I'm running, not a script, Ansible playbook, right now running is creating that topology in my MacBook. So let's see, this is really joy. So let me move on to them. Let's see. Still running, so it might take a little bit more time, but Let me see if I can. So right now, creating a OPS Docker instances using the frameworks. So since we are waiting. Yes. So right now, what I'm running is set up YAML framework. This is not specific to Ansible framework yet, but I'm setting up this Docker containers and copying the SSH key using the Docker compose component, and then setting up the network component here. Yeah. Okay, good. So right now, the topology I showed before, set up. But this is just Docker instances with all the network connections, and there is no, thank you, Diego. So there is no configuration. So let me log into the box. I set up some of the code mapping using the Docker instance. So I don't have any configuration at this point. I just created Docker instances and created network connections using the Docker new 1.10 Docker networking. And what I'm going to do is, so I have one which configure all the Docker containers in single configuration. I actually make what I'm going to type is just one command and play slightly YAML, and I'm going to show you the actual contents of this playbook as well as some of the host files. But with this configuration, I'm going to configure all the 6 switches on my laptop, which is going to have all the IP addresses and connected, and reachability is there. Let me see. So this one is running. And first configuring the spine switch, which is this switch. And the hotname is already changed. If I show run, all the interfaces are configured. Yeah, IP route is there. Interface configuration also there. And if I come back to the previous one, the public switch is already configured and now we're on the X switches. This one is 5. One also configured. IP address is there. This one H is also there. And since I set up the Docker networking, so the IP reachability should be there. So let me see. Finger crossed. ESA 2 is connecting to the public switch. The local IP is this. Yes. I'm just pinning into the local interface and this is the other box is the interface, and it has 1, 2. Reachability. Last night, I didn't sleep last night instead of. I'm so glad to have this live demo up and running. And I.
Don't do anything, don't do anything.
This one, the 2 is the interface connecting to the edge switch.
That's local.
Yeah, this one is local. You know, I'm a networking engineer. First, check the local IP is up and running, and the other one's also up and running. So, all the Docker instances are up running. Docker OpenSwitch instances are up and running. Let me get back to the slide. The demo. And Travis. And we are writing Ansible roles, and that is hosted on the GitHub. And GitHub has amazing CI environment. We can run all those CI continuously whenever we check in a commit. That run CI runs, kicks in, and provide all the CI result, which is open and simple CI on GitHub. So we have, so one of the challenge in this OpenSwitch environment and this Travis environment is you need to commit to trigger CI. And in OpenSwitch, we have a Git system to go through all those reviews before committing to the our Git repository. So at this point, I'm just running this Ansible role in my GitHub so that I can run this Travis CI up and running and show you this is set. I'm having all the test cases. So this is a test result. Another beauty of this is you can run multiple test cases concurrently. So if you have 1,000 test cases, you can run 1,000 test cases concurrently instead of serialized. So this one, you click this, and you click view log, you can see all the logs. And this one is using Ansible to check Ansible, to follow the Ansible philosophy. So we have a test Ansible playbook to verify our Ansible roles. That is the, and all the code, including today's playbook, hosted on the GitHub, and you can double check. I'm looking forward to get the feedback from the community so that we can improve. And also, this is unofficial. Yeah. Official one is on our review of the switch.net. And the role I use tonight is already on our Git review system. And you can set up your GitHub account to a Git system so that you can make a comment or some feedback. We're more than happy to have your feedback. And okay. What patch or pull request or whatever. So this is my EC on Docker is the one which has all the playbooks which I use. So if you go now and I have all the topology diagram as well, and the setup playbook is this is the one I showed you before. We want to use, as Diego mentioned before, we wanted to use that topology playbook, and I spent last week and a week before to use it, but because of one challenge, the Isabel support, I couldn't use it. So that's why I wrote this playbook, but that's not a good use case to showcase how Ansible is awesome. I wrote this playbook last night and I'm using it and it's up and running. So this playbook setup, create a Docker image, copy node SSH public key, and some shell script to map, as I think somebody mentioned that, map the interface from the standard namespace to a network switch namespace. And also taking care of network connection of those